We have already derived Lagrange's equation of the first kind, and here we would like to look at some examples of the applications of this equation. Let's consider the Atode machine. It is essentially a rotating wheel, and two masses M1 and M2, they are hanging from this wheel by an inextensible string. We also define this length vertically. It's essentially 1D problem. The masses they cannot oscillate, so they can only go up and down. So this distance we call it x1, and this another distance we call it x2, and all the distances are being measured from the top to bottom. So our positive change in x1 would be downward. Okay, that is the direction. We keep that in mind. Now we write down the constraint. The g would be equivalent to x1 plus x2 plus pi times r, and that is basically half of this length. So that gives us the length of the string, and this being inextensible, and this is also tau, in the sense the gravity is acting on M1 and M2. So this length is constant. Now if we apply the Lagrange's equation of the first kind on the first mass, then we write mass times acceleration. Here this is not a vector, simply because we are only working with a 1D problem, and minus the external force, which is m1g, the gravity acting on the first mass, minus lambda del g del x1. Del g del x1, if you look at g, it is essentially nothing but 1. So we just have lambda from this equation. If you do the same thing on mass 2, you will get identical terms, except m1 would be replaced by m2. Now it is straightforward to solve this equation with additional condition, which is coming from the constraint that x1 double dot is equal to negative of x2 double dot. So if you use that, then it is straightforward to calculate the acceleration of both the masses and the lambda 2. Now lambda is essentially the tension in the string. The negative sign means that it is acting upward. Okay, so it basically opposes the gravity. The next problem, which was also featured in the class test, we consider particles sliding on a hemispherical surface. So as such, the particle coordinates, suppose it is x and y, and then we also consider that this is making an angle with respect to vertical by an angle theta. Now staying back in Cartesian, the constraint relation is essentially the relation of a circle, that is x square plus y square minus r square is equal to 0. We are considering this to be a point particle, and we apply the Lagrange's equation of first kind. So mass times acceleration, that is straightforward, x double dot I caps plus y double dot j caps, minus the external force, which is of course acting along the negative j direction, negative y. So it is minus mg j caps, minus, this is the unknown part, the lambda, unknown quantity, and del g del r. So how do we calculate del g del r? For a vector, it's straightforward. Del r is essentially, like we mentioned, we take it to be I caps del x plus j caps del y acting on g. G is given by x square plus y square minus r square. So it would be twice x I caps plus twice y j caps. So if we substitute that in the equation above and equate all coefficients of I caps and all coefficients of j cap, after all I caps and j caps are orthogonal, so individually the coefficient of I caps and the coefficient of j caps must vanish. That condition gives us two equations, mx double dot minus twice lambda x is 0. The other one is similar, except we have the gravity too. Now it becomes easier if we choose a different variable to solve this, or rather to simplify this. One can in principle solve it using x and y, but it would be cumbersome. Much simpler is choose x to be r sin theta and y equal to r cos theta. If you substitute that and play around a bit of algebra, then you get the equation of motion to be theta double dot, the angular acceleration, is equal to g by r sin theta. That is expected. This is basically the component of the gravity acting this way. That should be responsible for the acceleration. And then we have the constraint that lambda, here we found it out, the lambda is equal to m g cos theta minus r theta dot square. So essentially a lambda gives us a idea about the force this way, force inward. I mean, you see gravity is acting downward, so component of the force is mg cos theta. And if the particle is sliding on a circle surface, cylindrical surface, or hemisphere, then this is the centrifugal force m r theta dot square. So their difference will tell us that which way the constraint force should be. In most cases, this value is less and this is more, so that the constraint force just balance the net force acting inward and the particles stay on the surface. Now, as the particle slides down, the centrifugal force increases, and at some stage these two would be equal, which means at the time the lambda would be 0, and when lambda is 0, there is no constraint force. The particle would be entirely free to fly off the tangent. So lambda equal to 0 gives us the condition for particle to be flying off. So this is how you do it, but you must check this algebra once more. I mean, it should be like this, but it's good to check once. Here we have the ladder problem. We already discussed a bit about it in the discussion forum, but let's try to apply the Lagrange's equation of the first kind. Now, ladder can be thought of like a rod, uniform, homogeneous. The trouble is, we just learned how to work with point particles, not an extended object. So we will approximate the ladder by a dumbbell. So we have 2 point mass m and m at 1 and 2 with coordinates x1 and y1. On the other hand, the second one here is basically x2, y2. So we write down the constraint. The first constraint is, of course, the length of the ladder is not changing, or length of the dumbbell is not changing, which means we have x1 minus x2 whole square plus y1 minus y2 whole square minus l square to be 0. The second constraint is x1 equal to 0. So that means this mass, first mass, is moving along the wall, vertically down. The third constraint, G3, is equivalent to y2 equal to 0, which means the second mass is not lifting from the ground, it is basically following this line. So these are our 3 constraints. So for first point particle, we write down the Lagrangian equation of the first kind, mass times acceleration minus the external force, which is gravity acting downward, minus lambda 1, and here is the del G del R1, which of course if you calculate, I mean del G1 del R1, so if you calculate it from the first gradient, it is straightforward. You will get something like 2x1 minus x2 I caps and plus 2y1 minus y2 j caps. But of course, for further to proceed further, you can use the other constraints to simplify it, which means x1 would be 0 here and y2 would be 0. And similarly, in this equation, the first term, remember, it is basically x1 double dot plus y1 double dot with I caps and j caps, of course. Now, because x1 is 0, x1 double dot is also 0. So, this acceleration is essentially only downward acceleration from y. But we are not done in this equation. There is still something from g2, because g2 is function of the first coordinate. So, del g2 del r1 will give us just lambda 2 along I caps. Okay. So, we collect all coefficients of I caps and j caps and equate them to 0 to get the first equation: mass times downward acceleration plus mg minus 2 lambda 1 y1 is 0. Second equation is an algebraic equation. There is no acceleration involved. Twice lambda 1 x2 is equal to lambda 2. For second point particle, you have similar set of equation. On the in the first equation, you see mg is involved, and gravity is playing a role. In the second equation, the gravity is not directly included, but of course x2 is connected to y1 through the constraint. So, gravity is indirectly coming through the lambda 1. You see, the lambda 1 is basically the constraint force. The first mass is going down, but because they have a constraint, as a result some force is being applied to the second mass, which is responsible for horizontal acceleration. So, you have to have some kind of force acting on it coming from the first mass. That is basically our so-called constraint force along the radar. Okay. Now, this constraint force along the radar and all, this is our third equation, and this fourth equation, again an algebraic relation between y1, lambda 3 and gravity. Now, again we can do a variable substitution. We can define an angle phi with respect to horizontal, and then you see, our relation, if you look at all three constraints, then x1 is 0. So, our constraint relation looks like x2 square plus y1 square minus L square is 0. This is the equation of a circle. So, in principle, we could have assumed like x2 equal to some cosine phi or sine phi. In this case, we are assuming x2 to be equal to L cos phi and y1 to be L sin phi. So, if you assume that, then the equation is again simple. Phi double dot is equal to minus g by L cos phi. Straightforward. This is your equation of motion. Okay. Although it's a fairly complicated, it's not solvable directly, and numerically one can solve it. But you look at the lambda again. So, what you have as lambda is mg by L sin phi minus m phi dot square. So, obviously the constraint force lambda 1, that undetermined multiplier, tells you a little bit about constraint along the ladder, along the dumbbell. So, one part is obviously component of the gravity. We can see that. The other part is centrifugal force. How come we get a centrifugal component like this? Simply because if you are sitting at the center of mass of the dumbbell, then with respect to you, dumbbell is rotating. There is no doubt about that, because this dumbbell was vertical at t equal to 0. Suppose this is where it started from. Not exactly vertical, it's very close to vertical. And then finally this mass will come down, so it would be horizontal. So, there is definitely some rotation of this dumbbell is involved. So, if it rotates, then the phi is changing. So, consider a dumbbell which is free. First you consider it's free. A freely rotating dumbbell means both the masses are trying to fly off with like m r phi dot square or m L phi dot square, some centrifugal force. So, there has to be an inward tension to balance that, to keep the mass not flying off. Okay. So, that component has to be there. It is there, and moreover there has to be a component of the gravity. So, in this problem the constraint force represents both of them. and they are acting along the ladder. How do we know that they are acting along the ladder? Look at the full expression. Full expression in the sense without applying G2 or G3. If you look at the full, this is essentially along the line joining x1, y1 and x2, y2. Even if you apply the constraint like the G2 and G3, no problem. Even then, this is along this line. Okay. So, we have three constraint forces, G1, G2, G3 and all. Now, often, remember this ladder problem is often solved for static cases. So, that means you have friction up there, you have friction here, the ladder is not moving. In that case, how do you calculate the equilibrium condition, whether the ladder would be stable or not? I mean, but remember, that is a separate problem. In that problem, we will have this phi dot component vanishing, but the components can be analyzed in this manner, but we will take up this problem later. We have also came up with Lagrange's equation from D'Alembert principle. Now look at some simple examples. Say we take a free particle. For a free particle, the kinetic energy is simple, half m r dot square, which of course we can write as half m r dot r dot. It's a dot product. And for a free particle, no potential in it, we know that. So the Lagrangian is simply t minus b, that gives us half m r dot square, and that's the whole Lagrangian. What about generalized coordinates? We are supposed to choose some, but in this problem it's a free particle, so there are no constraints, which means that it has 3 degrees of freedom and we are free to choose any 3 coordinate, orthogonal, independent, and that can act as generalized coordinate. We choose, let's say, x, y, z. Q1 is x, Q2 is y, Q3 is z. The remaining part is straightforward. If you just calculate for one, you will get all others because all are symmetrical and kind of same. So, rate of change of mx dot, which is the momentum along the x direction, is 0. So, which means the momentum along x is conserved, so is along y and z. So, free particle, that is standard result, except we did it from the simple Lagrangian. But then free particle is a too simple example. Let's make it slightly complicated. Let's consider a particle which is moving in this plane under gravity. So it's a 2D problem, not a 3D problem yet. So the kinetic energy is half m r dot square, which is nothing but, r dot square is basically x dot square plus y dot square. And the potential, because it has height mgy, generalized coordinate we choose x and y because there are no other constraint here, so we are free to choose this. And then ddt del L del x dot minus del L del x, our Lagrange equation for x gives us the x momentum is conserved and x acceleration is 0. And for y, it is simply the y acceleration is negative of g, exactly what we expect. So it gives us in a straightforward manner, starting from the kinetic and potential energy, it gives us the equation of motion. What about 1D springless system, where we have a mass moving horizontally connected to a rigid wall by a spring of spring constant k. The kinetic energy, we write it as half mx dot square, and the potential energy half kx square. Now, where is x measured from? So, where did we choose the origin? Origin is the equilibrium position of the mass. So, that means if nothing is moving, wherever we find the mass to be when spring is not compressed, not stretched equilibrium, we call it x equal to 0. And then, of course, with respect to, with that definition, potential energy is half kx square, and the Lagrangian is half mx dot square minus half kx square, straightforward. And the equation of motion, if you just calculate the Lagrange's equation in this case, you get mx double dot plus kx. We all know, it's straightforward. And also we can look at a simple pendulum where the constraint is again x square plus y square minus L square is 0. So we are assuming this pendulum, this bob, is connected to a rigid support by a massless rod of length L, and it's moving in this plane. So x, y are two good coordinates, but then there should be only one generalized coordinate. After all, you see there is a constraint. So we choose generalized coordinate to be the angle, the only variable which is changing for this problem. So kinetic energy is half m x dot square and y dot square. If we move that to in terms of r and theta, then it should be half m r dot square plus r square theta dot square. So I mean, like this should be r square. Okay. And the potential is minus mg r cos theta, which came from mg y. I mean, it looks negative simply because we are measuring the distances from this origin, so y is downward. So this is why the potential energy comes out to be negative. Now, if you just evaluate Lagrange's equation for theta, well, theta is the generalized coordinate here. So for that equation of motions, we get it after just one or two lines of algebra, that angular acceleration plus, I mean, theta double dot plus g by r sine theta is 0, our familiar equation. But then we just started from Lagrangian this time, a simple doing this. A pendulum with a straight spring as the rod. This is basically a mixture of the two previous examples, a springless system and the pendulum. So here we have a spring. It is straight. It is straight spring. And here is the bob. So let's suppose this distance is r and this angle is theta. Now here, how many generalized coordinates we have? I mean, there are no constraints because this distance is not fixed anymore. So x, y could be chosen, or we choose r and theta because it would be simpler. Now, how did I know that it would be simpler? Well, you see, suppose r is fixed, which means instead of spring, we are talking about a straight rod. For that problem, if we use x and y, we'll get equation for both of them, but they will be coupled in the sense that there will be a constraint connecting x and y. On the other hand, if we use theta, we'll get a single equation. So that means the r and theta are two natural variables. Keeping one constant will give us a naturally one equation for the other one, not like a mixture of x and y. So this is why we choose r and theta. With these coordinates, the kinetic energy is straightforward. Half m r dot square, rate of change of r, and this r square theta dot square. And potential energy is, of course, like the simple pendulum case, mg r cos theta with negative sign, that part is there. But this time we will also get something from the spring. This should be half k r minus r naught square, where r naught is the equilibrium distance. So that means that if there is no gravity and the spring is just held static, then whatever the length of the spring is, let's say that is r naught, then with that, I mean, we can write the potential energy of the spring. Now we have two variables r and theta. So with respect to r, we find the equation to be mass times r double dot. It has two components. One is a component of the gravity, which is mg is acting downward, but mg cosine theta is acting kind of along the spring. So that is responsible for a stretch. So that is there. And the spring force, which is acting opposite, meaning it is along the spring again, but towards the support. So this is why the two forces come with a opposing sign. So r double dot acceleration would be directly proportional to this if we take this mg cosine theta term on the other side, and this will come with a negative sign just to indicate the spring is kind of compressed. I mean, this is a restoring force. So the dynamics would be interesting, let's say, because now we have theta 2, and the theta equation is kind of straightforward. It says mass times ddt of r squared theta dot. If the mass is not a function of time, suppose we push the mass in, not a function of time, then basically we are saying that rate of change of this term is nothing but angular momentum, m r squared theta dot. So this angular momentum should be, its rate of change should be given by the torque. And what is the torque? Well, mg is acting downward and this is mg sine theta. So mg sine theta, or rather this distance is r sine theta. So this is r sine theta. So r sine theta times mg, that will give us the torque of torque of rotating the spring about this support. So that's a straightforward equation. The two equations are coupled. The dynamics could be fairly complicated. Of course, you can see the situation is not exactly simple, but at least we know how to deal with this, and our terms match intuitively with the what we expect from what we expect intuitively matches with the Lagrangian formulation. Another example of a spring is, consider a rotating spring. So basically consider this axis, and here is a spring and there is a mass. The spring is massless, of course. This is horizontal, it is kept horizontal, and the spring is being rotated with angular speed omega about this axis. So if you call it z axis about z, the spring is rotating in the kind of xy like plane. And we have to find the equation of motion. So what we do is, first we identify the generalized coordinate. You see it is rotating but with a fixed omega, so that means the only parameter that can change is this distance r. Right? Usually the angle of the spring, and the spring makes an angle while it rotates with x-axis. So that angle is predetermined. That angle, because we are rotating with omega, that angle is not changing. It's not a free dynamical parameter. It is already premediated by the motion itself. Anyway, just write down the kinetic energy. This is essentially a planar motion. The spring is moving on a plane. So let's suppose we are calling r and theta. R is this along the spring and theta is the rotation of the spring. Then kinetic energy is half m r dot square plus r square theta dot square. But then theta dot is already decided omega. So instead of theta dot, we write omega. This is what I meant by premediated. And now potential energy is just the spring force, half k r minus r naught square, where r naught is the equilibrium position when omega is 0. That means spring is held static. And we apply Lagrange equation with r, our generalized coordinate, and what we get is mr double dot, mass times acceleration, is equal to the centrifugal force mr omega square and minus the spring force. Spring force is acting inward. Okay. So that is again intuitively quite clear what it should be. Now, what if it is not premediated, meaning it had some initial angular velocity, but then we are not trying to keep omega fixed. Suppose it is theta dot, meaning we just let it change as it is. Then what would be the dynamics like? Well, if omega is like theta dot, then the only place where theta dot will appear is in the kinetic energy. Potential energy will remain unchanged. So in the equation of theta dot, you see, theta does not appear in the Lagrangian. So del L del theta would be 0. But del L del theta dot will give us m r squared theta dot, and its rate of change should be 0. So angular momentum is conserved. This is again the statement of this equation, meaning of this equation. Now what does it mean? It means if the distance increases, the r increases, then theta dot must decrease, speed will be slower, or when the r comes, r is smaller, the mass comes in, then theta dot should go up. So as you can see, it's fairly complicated dynamics in the sense that this mass is free to oscillate along this direction. Whenever it comes in, the theta dot changes, but then theta dot changes means you expect the centrifugal force m or theta dot square that to change. Yes, it will change. So I mean that will in turn change the behavior of R. So it's a very interesting problem, let's say. I mean we will not discuss it further, but I mean of course it might be possible to look at it numerically, and that would be interesting. So these are more or less the set of problems that we typically work with. Now you need to definitely practice. I mean each of the examples that I worked out here, you should do it starting from the scratch in your notebook. Check all the expression because there could be mistakes. There are set of problems in Goldstein's books exercise which I strongly encourage you to try them out, and also I will try to make a list of representative problem of Goldstein. I mean Goldstein has many problems, although the solved examples are available, but still not all problems are of equal difficulty or offer you something new. So as such, I'll try to give you a list of problems apart from whatever I show you here.